What's up, guys? It's me, Sir Ernest, and today we will discuss a sample problem related to Lagrangian dynamics. The problem reads, a simple pendulum of length B and bob with mass M is attached to a massless support moving horizontally with a constant acceleration A. Determine A, the equations of motion. Okay? So we're only going to focus on letter A of problem 7-13. Okay? So first, let's write the problem, or let's illustrate the problem. So for example, let's say so let's say this is your x and y axis. So that means this is your origin. And let's say at any given time t, the particle is at this position. And this is where your support is located at x. Sorry, at x1. Okay, so this is your support. Okay, and this support is moving horizontally with a constant acceleration. So let's say that acceleration is in this direction. Okay, and this acceleration is constant along x. So this is at a, say, I hat, and this is a constant. Okay, now from this support we now draw our pendulum. So let's say here, so this is our pendulum bob with mass M and length B. So sorry, so we can define the following. Number one, we can define this angular component or angular position. Okay, and then let's say from the y-axis we define x1. Okay, and let's say the position of this pendulum bob will be x. And then with respect to this line, this pendulum bob is x2 away. And then this will be your y. Okay, so this is our setup. Now, so from here we can define the following coordinates. So the coordinates of the bob will be x, y. Okay, so that's x and y. Now your x in terms of x1 and x2 is given by x1 minus x2. Okay, so x1 will be the position of the support, and it moves with a constant acceleration. So that means, let's say this particle moves from the origin from rest. So therefore, the position x1 will be equal to 1/2 a t squared. So again, x1 is 1/2 a t squared from your uniformly accelerated motion. Now x2 on the other hand will be minus b sine theta. And then y will just be negative b cosine theta. So b cosine theta. Okay, so from here we can calculate the velocity. Velocity would be AT minus B theta dot cosine theta. And then y dot would be equal to B theta dot sine theta. Okay, so from here we can assemble our Euler Lagrangian of the bob. So the Lagrangian of the bob, okay, so the Lagrangian of the bob will be T minus U. T is 1/2 m x dot squared plus y dot squared minus m gy. Okay, so noting that the kinetic energy is 1/2 m v squared, and then your potential energy is mgy. Okay, so putting everything together, we have 1/2 m times the square of x. So square of this, we have square of this, we have a squared t squared plus b squared theta dot squared cosine squared theta minus 2 ab theta dot t cosine theta plus square of this is b squared theta dot squared sine squared theta, and then square and then mgy. Y is negative b cosine theta, so this is plus mgb cosine theta. So this should be here. Okay, so therefore the Lagrangian is now equal to, so this one can be combined with this one using the Euler form, using the identity cosine squared plus sine squared theta equals 1. Okay, so now you can rewrite the Lagrangian as 1/2 m times a squared t squared minus 2 ab theta dot t cosine theta plus b squared theta dot squared plus mgb cosine theta. So this is now your Lagrangian, and we can see that the Lagrangian is only a function of theta dot, and both are functions of time. So this tells us that we only have 1 degree of freedom, which translates to 1 equation of motion along the theta direction. Okay, so let's do this. Okay, so if that is your Lagrangian, okay, so the Euler-Lagrange equation is now given by partial derivative of L with respect to theta, and this is equal to total derivative with respect to time of partial derivative of L with respect to theta dot. Okay, so partial derivative of L with respect to theta is, okay, so this is theta and this is theta. So that's m AB, so that's MAB theta dot T sine theta. Okay, so minus, so that's plus. Okay, and then also this one, so this is minus mgb sine theta, and this is equal to the total derivative with respect to time of partial derivative of theta of L with respect to theta dot, which is this and this. So we have negative distributing m and 1/2 here, so that's m a b t cosine theta plus m b squared theta dot. Okay, so let's cancel some common factors. So we have m is constant, so we can cancel it here, as well as b is also constant. Okay, so we now end up with a theta dot t sine theta minus g sine theta equals derivative of this with respect to theta, because theta with respect to t, so this is t and cosine theta. Theta is a function of time. Okay, so we use product rule and then chain rule. Okay, so that this is now equal to negative a cosine theta plus a t theta dot sine theta, and then this one, derivative of this with respect to t would be plus b theta double dot. Okay, so now we can now simplify this by number 1, canceling this with this, right? Okay, so now we're left with 3 terms, this term, this term, and this term. We can simplify this by writing b theta double dot equals g sorry, that should be that should be a cosine theta minus g sine theta, or theta double dot equals a over b cosine theta minus g over b sine theta. So this is now your equation of motion. Okay, so if we're going to look at this equation again, let's rewrite our problem. Okay, so this is your support, and this is moving with a constant acceleration, and then this is your pendulum. Okay, so remember, this is your particle. Now, if for example the particle, the support is not moving, so that means a is equal to 0. Okay, so support not moving. Okay, or at least moving in a constant velocity. But the point is that if a is equal to 0, so this term would be equal to 0. So theta double dot will now be equal to negative g over b sine theta. And this gives you your simple pendulum equation of motion. Okay, so if the support is not moving, this system will behave as a simple pendulum. Now, on the other hand, if the if for example the particle is along this axis, okay, sorry, let's say the theta is theta is 0. Okay, so that means the particle is not moving, it's here. Okay, it's here, so theta is equal to 0. So if theta is equal to 0, this equation, okay, so theta double dot will be equal to A over B cosine 0 minus 0. So this is 0. Now, because theta is equal to 0, so therefore theta double dot is equal to 0. Okay, so that means there is no, even if this particle moves here, the angular direction, the equation of motion along the angular direction will not have any equation of motion. Okay, so that's it, simple. Okay, so this is now the equation of motion of a simple pendulum that is attached to a massive support moving horizontally with a constant acceleration. Okay, so thank you for watching. I hope you learned something today, and I will see you guys in the next video. Bye bye.